This part explains what a molecule really is at the structural level, and why that single idea seeds the whole book. A molecule reduces to one thing, the spatial ledger of where its valence electrons sit. Everything. The chapter builds, Lewis structures, formal charge, resonance hybrids is a single move, bookkeeping that distribution and ranking which arrangement holds electrons more stably. Carbon earns the chemistry of life through its tetravalent reach. 4 bonds, catenation, stable frameworks for DNA, protein, and sugar. The claim of a vital essence does no work here. Carbon's bonding reach is the whole story. Weyerhaeuser's synthesis of urea from ammonium cyanate is the anchor that kills vitalism. The line between organic and inorganic was only ever carbon's bonding reach, never a life force. This seeds the book's whole arc. One structure is an electron map graded by stability. Every mechanism ahead becomes electrons flowing toward the more stable distribution. This section explains why a chemical name is an invertible serialization of a molecular graph. Carty's whole chapter turns on the two-way arrow he states outright. Structure gives you the name, piece by piece. The name gives you back the structure, piece by piece. The generative move is this. Fix a canonical parent chain. Its length picks the root, meth, eth, prop, and onward. Its bonding picks the suffix an. Number that chain into an axis, then list every deviation from bare hydrogen as a pair of a locant and a prefix. Chloro, nitro, alkyl, 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 alkysy. The compound's identity is thus a coordinate string over one chosen backbone. Learn the grammar once, and every alkane, haloalkane, cycloalkane, and ether reads off the same address system. The later functional groups only add a suffix slot. This section explains why a molecule's physical behavior can be predicted from its shape. A molecule's bulk behavior follows from its shape rather than its formula. BSEPR fixes geometry from electron group repulsion. Geometry plus functional groups fix whether the molecule is polar. Polarity fixes which intermolecular forces operate: dispersion, dipole-dipole, and hydrogen bonding. The strength of those forces is exactly what boiling point, melting. That is the whole chapter. Composition becomes geometry. Geometry becomes polarity. Polarity becomes force, and force becomes property. With each arrow, the chapter's opening. Datum carries it. Carbon dioxide and formic acid sit at 44 and 46 grams per mole, yet they boil at minus 78 degrees Celsius and 101 degrees Celsius. Equal weight, opposite behavior. The difference is force, not mass. Predict any new molecule by walking the same chain. This section explains how a chemical bond arises from treating electrons as waves. A bond is a superposition. Treat electrons as waves, and everything follows from a single operation. Add atomic orbitals as functions, tracking phase. Same phase overlap, reinforces, which is bonding. Opposite phase overlap cancels, which is anti-bonding. The chapter runs that one operation at 2 scales. On a single atom, mixing s and p orbitals re-chooses the basis to point where bonds actually go, and that is hybridization. Across atoms, combining those hybrids builds the molecular orbital the electrons occupy. Lewis structures and Z-separ give geometry but carry no phase, so they cannot say why ethene refuses to twist. Phase is what supplies the answer. Pi overlap vanishes under rotation, and the energy of that lost overlap is the rotation barrier itself. This section explains how naming alkenes, alkynes, and benzene derivatives extends the naming procedure you already run. A name is a canonical address for a structure. This interchapter adds one rule to the alkane algorithm you already run. The unsaturation outranks everything beneath it. The carbon-carbon double bond, or the carbon-carbon triple bond, must sit inside the root, so the longest chain containing the bond wins. Even over a longest chain containing the bond wins, even over a longer chain that misses it. Numbering starts from whichever N meets the multiple bond first. Substituents only break ties. Benzene enters as 3 carbon-carbon double bonds, the same family. The whole of nomenclature is one primitive, a fixed priority order over structural features, each tier fixing the name only where the tier above it ties. This section explains how isomerism gets classified. Sameness of molecular formula defines an equivalence class. The word isomer names a relation within that class, not a single molecule. Cardizontel is the question, John is a cousin of whom? The chapter's work is the classifier. One decision tree, shown in Figure 4-1, partitions that class by how 2 members differ. The first question asks whether they share the same connectivity. If the answer is no, the 2 are constitutional isomers, and the bonds themselves differ. If the answer is yes, they are stereoisomers, which split further. The next question asks whether they differ only by rotation about single bonds. If yes, they are conformers, and here is the surprise. Conformers form a continuum along a dihedral angle, interconverting freely, so they generally cannot be isolated. The whole structure is a quotient, refined by a decision procedure. Every later isomer type is just the next branch of the same tree. This section explains chirality and how a molecule's handedness governs its behavior. Handedness is the whole chapter. A tetrahedral carbon carrying 4 distinct groups has a mirror image that cannot be rotated onto the original. That property is chirality, defined by the absence of an internal mirror plane. 2 such mirror twins are called enantiomers. Mere identical molecules that fail to be mirror images are called diastereomers. Here is the surprise that carries the rest. Enantiomers share every scalar property, including bond energies and melting points, so only a chiral probe can tell them apart. Plain polarized light does this optically. The body does it lethally, because its enzymes are single-handed. Thalidomide is the anchor. One enantiomer settles nausea, while its mirror deforms limbs. From this, you can predict everything else. Stereochemistry counts symmetry rather than composition, and a mirror plane is the switch. This section explains how a molecule's 3-dimensional handedness gets turned into a single spoken label. A molecule's handedness is a geometric fact, and naming it means collapsing a 3-dimensional arrangement into one discrete label. The move is this. Impose a total order on the substituents around a center by the Kahn-Ingold pre-log priority rule. Rank by atomic number, break ties 1 shell outward, then let the geometry read out a sign. At a tetrahedral carbon, point the lowest priority group away from you and watch the remaining 3. If they descend clockwise, the label is R. If they descend counterclockwise, the label is S. At a double bond, ask which side the 2 higher priority groups sit on. Together on the same side gives Z. Across from each other gives E. 1 primitive, 2 anchors. Rank, then read the rotation or the side. The same ordering that fixes handedness at a point fixes it across a bond. This section explains the proton transfer reaction, the simplest reaction in organic chemistry, and why learning it teaches you to read every later mechanism. A proton settles wherever the negative charge it leaves behind is most stable. That single rule is what the chapter installs. Equilibrium favors the more stable charge, hence the weaker acid and its more stable conjugate base. It installs that rule on organic chemistry's simplest reaction, precisely so the machinery generalizes. Curved arrows track the two electron pairs, the quantity pKa measures the tendency, and charge stability predicts pKa from structure alone with no table needed. Learn proton transfer, and you have learned to read every later mechanism as the same question. Which way does charge prefer to settle? This section explains how every reaction in 16 chapters reduces to a small, fixed set of elementary steps. Nearly every reaction across 16 chapters collapses to a closed alphabet of 10 elementary steps, proton transfer plus 9 others recombined. That is the whole compression. Mechanisms are strings over a tiny generating set, so mastering the set subsumes the reactions. Each step obeys one law. Electrons flow from an electron-rich site to an electron-poor one driven by charge repulsion, relaxing into attraction, the same gradient the bee and pollen opener draws. The pairing structure tightens it further. Coordination and heterolysis, the two additions and the two eliminations, are each a step, and its exact reverse, with one factor governing both. Learn the alphabet and its single driving force, and you can predict an unseen reaction rather than memorize it. This section explains how one orbital move underlies both molecular stability and chemical reactivity. A filled orbital, overlapping an empty one, splits into two. The electron pair drops into the lower one, and stabilization is guaranteed whenever occupancy is asymmetric. That single move is the whole chapter. Read at rest. It is hyperconjugation. An adjacent carbon-hydrogen sigma pair leaking into an empty p orbital of a carbocadiontal or into the pi star of an alkene, so each alkyl group buys stability. Inductive donation was only the surface story. Read in the transition state. The same overlap is frontier orbital theory. One reactance HOMO feeding the other's LUMO lowers the barrier, and the reaction is allowed. Stability and reactivity are one mechanism clocked at 2 moments. The curved arrow you already draw from the rich site to the poor site is HOMO into LUMO. This section explains how a compound with several functional groups gets named when one of those groups demands a suffix. A molecule carries many functional groups, but the name grants exactly one of them. The suffix, a fixed priority table, here ranking all above. Amine above the ketone and aldehyde ordering picks the single winner present. That winner does 3 things at once. It fixes the parent chain, it becomes the suffix, and it claims the lowest locant, so numbering runs from whichever end reaches it first. Every loser demotes to a prefix substituent, forms like amino and chloro, ranked only alphabetically and blind to locant. So naming is a deterministic sort. Then anchor, rank the groups, crown the top one, orient the chain around it. The compound, 5-aminopentan-1-ol, is the whole rule in miniature. The OH hydroxyl group wins the suffix and takes carbon 1, while the NH2 amine becomes a mere prefix. This section explains the shortest multi-step reactions, SN1 and E1, and what their names actually count. Reactions are built from a small alphabet of elementary steps, the way letters build words, and that is the chapter's own figure. SN1 and E1 are the shortest interesting words in that alphabet, 2 steps each. Here is the generative primitive. The number in each name counts the molecularity of the rate-determining step, meaning the count of molecules that come together in the single slowest step. It does not count the steps in the whole mechanism, and that is exactly where the name misleads. SN1 and E1 both bottleneck on one unimolecular event, the leaving group departing to form a carbocation. So both are first order, and both are blind. The rate law is therefore a fingerprint of the slowest step alone. Predict the rest from that. The same rate-limiting step means the same kinetics and a shared intermediate. The fates diverge only afterward, substitution or elimination, decided once the bottleneck is already passed.